many more functions are going to be taken place to get the that means the new structural layers to form the mechanical and electro mechanical devices.
Hello. Hello.
Hello. Yes,
Ma'am, slides are not moving, ma'am.
No, I'm not moving the slide. I'm on the introduction to micro electromechanical system, ma'am. Yeah.
Okay, ma'am. Fine. Okay.
Yeah. So it is even more interesting if MEMS can be merged, and not only with microelectronics but with other technologies such as photonics and nanotechnology also, right? So this is the brief introduction about MEMS technology and what are all the advantages of microelectromechanical systems. Right. So here I am not going to, directly going to the advantages of microelectromechanical system. I'll just give one example. So with that example, you can understand what are all the advantages of this system or technology, right? So the example is like this. So why can't we write the entire, that means everyone is aware of encyclopedia, right? So if you take encyclopedia, it consists of 24 volumes. So all these 24 volumes, why can't we write on the head of a pin? You know, this statement was written by Richard P. Feynman. All the 24 volumes you need to write on the head of a pin. Is it possible? Question. Right? No, not at all. But if you go with MEMS technology, it can be possible. So how it is going to be possible? So if you take the head of the pin, you know the size of the head of the pin? It is a 16th of an inch. 16th of an inch. If you magnify it by 25,000 diameters, the area of the head of the pin is then equal to the area of all the pages of the encyclopedia. You just imagine 25,000 diameters, 25,000 diameters. If you magnify the head of a pin, then that area of the head of the pin is then equal to the area of all the pages of the encyclopedia. So therefore, all it is necessary to do is to reduce in size all the writing in the encyclopedia by 25,000 times. Is that possible? Next question. Right? So that is the encyclopedia on the head of a pin. How? Let's consider all books in the world and say that there are some 24 million volumes of interest in the world. So if you would take, of course, the area of about a million pinheads, because instead of there being just the 24 volumes of the encyclopedia, there are 24 million volumes. So the million pinheads can be put in an area of about 3 square yards. Then the silica replica with the paper thin backing of plastic with which we have made the copies, and with all this information in an area of approximately the size of 35 pages of the encyclopedia. So all this information which all of mankind has ever recorded in books can be carried around in a pamphlet in your hand and not written in code, but a simple reproduction of the original pictures, engravings, and everything else on a small scale without loss of resolution. So this is the beauty behind this MEMS technology. So And even today, each and every application, if you take, it is that means MEMS technology is present. Okay, so in this direction, if you look at the miniaturization, you just see the best example is like the computers, digital computers. So in 1946, how our computer was, it is almost occupied a room, right? So then from this 1996, we have laptop, and that laptop size is almost 10 power 6 times reduced, and then palm top. So all these spectacular changes, that means miniaturization, took place during 50 years of span time, right? So, and at the same time, mobile phones, you can also take the mobile phones. So that means finally, the only solution is to pack many miniature function components into a single or small device. So that is our ultimate goal. So if you take the different applications of micro electromechanical system, so you have several applications. What area, that means where it is not present, you cannot imagine. So if you take aerospace, it is there. Automotive, it is there. Biomedical, it is playing a vital role. Chemical, optical displays, communication, and whatnot. Wireless, that is, and optical communications, space and defense. Any application you take, so everywhere MEMS technology is involved. So in that direction, you just go take this diagram. So here, MEMS or NEMS applications, you just see all the areas has been covered in this single diagram. So here, this MEMS technology is interdisciplinary. Anyone can join and anyone can do anything. That means miracles also. So initially, I have just quickly go through the automotive applications, because everyday's life we are seeing all these things, but we don't know what is inside of that. So every day we are using the cars. So in cars, each and every part, if you take, so you have MEMS technology, right? So in the similar fashion, you just take even tires. So for pressure monitoring, we are using a sensor, and that sensor comes under the MEMS technology, right? And if you take the car's airbags, so airbag, when it is going to open, whenever it is going to crash, that means our car is going to crash, airbag is going to be opened. So in this airbag also, we have the MEMS technology, that is the crash sensor. It is present inside the airbags, which is going to inflate, right? So from that, nitrogen gas is going to be released. With that, the balloon is going to be opened. So that is MEMS technology, right? And if you take aerospace applications, nowadays most of the people are traveling through air. So if you take aerospace, so pressure sensor belt on jet planes, which is made with MEMS technology, right? And even if you take the helicopter, so even in that, we have the aerofoil section with smart skin, right? So all these things are made with MEMS technology. Okay, so and jet engines, the strength of the jet engine, or we can say that the life of the jet engine, health of the jet engine is going to be measured with the MEMS technology, or monitoring taken place by the MEMS technology, right? So health monitoring of jet engines. Okay, so Now come to the medical applications. So here you have several applications in medical where I just given previous applications or just brief that where you will get aware of awareness on MEMS, right? So once if you come to the medical applications, so here also we have lot of different areas we are going to use this MEMS technology, and how we are going to use this MEMS technology in various health conditions. We are going to use this MEMS technology, right? So if you take the personal health monitor, where it is going to receive and analyze the data from a number of sensors, like example ECG, EMG, blood pressure, pulse oximeter, and even it is going to measure the glucose levels, and it detects the cancers, various kinds of cancers, and general health monitoring, and tracking and monitoring of doctors and patients inside the hospitals. Apart from this, you will have the intelligent pill, where it goes inside the body and it detects all the diseases. And if you want to remove some diseased area, so there also this MEMS technology, using MEMS technology, you can remove the diseased area. So nanorobots, for example, so which are going to work for a blood vessel to remove a cancerous cell. So microactive forceps, right? So that is microactive forceps. So what for we are going to use this? For retinal surgery, right? And smart tongue for food packaging and electronic nose. So all these comes under medical applications. So for example, one by one, if you take the problem is broken bones. So simply why madam is saying that broken bones, right? So the problem inside the broken bones, if you take, so few cases, or sometimes you can experience that there are complicated breaks which has to be operated. So during these operations, the plates and screws are often used to hold the bones together. So in that direction, in that case, to prevent a second operation, surgeons prefer to leave the plates and screws in after the bone has healed. But sometimes the body's immune system attacks these screws and plates because they are made of tissues. So in this case, screws and plates need to be taken out. So you have to go with second operation, so which is going to be a costly and takes a long time to recover from that. You just remember, right? But what is the solution? MEMS technology came into the picture. So solution is diamond coating. So what is this diamond coating? Right? So here the nanotechnology enable the development of coatings. So among all the coatings, the normal materials with the ultra strong capacity is going to be like a diamond coating. So if you can take the example of this. For example, you are coating with a layer of nano-sized diamond crystal, right? So which is having a thousandth of a millimeter thick. So this coating can be applied to many different inorganic surfaces. And when you are applying this in different inorganic surfaces, the good news for using this coating in medical applications is that our bodies are less likely to reject something that is coated in the diamond crystals. So why? You know, because diamond is a pure form of carbon, and so our bodies. Right? So then, take the next problem, that is bone grafts. So whenever bones are going to be damaged, our body receives the message, that is via growth factor, which is going to repair. That means that repair is required. So sometimes our bones need help to repair themselves. So this is where a bone graft comes in. So the
Hello,
most common use of.
ma'am. No images are displayed, ma'am.
No, for
It's
this,
empty.
yeah, it will
No,
come
even
now.
in the previous also the
Previous there
images
is
were
no.
not there.
No, previous one there is no image, ma'am. It is like a, yeah, theoretical discussion.
Okay.
Yeah. So here, uh, the most common use of a bone graft is to stimulate the healing of bone. So the bone graft is used similar to fertilizer that stimulates the bone to heal and speeds up the process. So, doctors can either use the patient's own bone or a donor's bone. For example, if bone is taken from a donor, then there is a risk of the body's immune system attacking the tissues. If bone from the patient themselves is going to be used, then this means more operations for the patient. So that means it has potential complications. And if the bones are going to be very weak, where the donor bone has to be taken. So in that direction, so to avoid these complications, we are going to propose the carbon nanotubes. So these carbon nanotubes are in the same structural family as the buckyballs, but rather than a spear shape. These are cylindrical in shape. So nanotubes like buckyballs are made up of carbon atoms and are very light, but it is having a strong, that means it is very strong. So they make an excellent scaffold for tissue to grow on. So even in the future, the nanotubes could possibly be injected into our bodies. Right? So the next problem is targeted drug delivery. So how to deliver the drug to the targeted areas? So if we are not going to deliver the drug to the targeted areas, what will happen? Right? So the problem here it is being able to deliver a specific drug to a specific location, which that itself it improves the treatment speed and effectiveness. So in order for targeted drug delivery to work, so two conditions must be met. So one is the carrier must have internal space that can carry a drug, and the other one is carrier must have attachment points tailored for its target location. So in this direction, for this problem, so we are going to use buckyballs. So which consists of 60 carbon atoms which are arranged in the shape of a football and are absorbed into the bloodstream very easily. So they are extremely stable and have 60 attachment points. So each attachment point is for one carbon, you have one attachment point for other molecules. So one example you can consider you could be attaching an antibody to the buckyball because they are hollow. They can also encase molecules. So that is the beauty behind this buckyballs, right? So then next problem is disease diagnosis. So it is nowadays it is very difficult. Previously, with the pulse, the doctors used to say what is the problem inside the body. But nowadays it is very difficult. We have many equipments under. If we are going under that, then only the doctors are going to say these are the problems, even though it is not 100% correct. So in that direction. So if you take the modern medicine has moved very quickly in the last few decades, and diagnosing disease can still be a complicated and time consuming process. So doctors usually have to do a lot of tests to find out what is wrong with someone. This is not only stressful for the patient, but it is also costs a lot of money. So in that direction, the solution for this problem is microcantilevers. So here, the microcantilevers are a bit like a tiny diving boards on a microchip, and these are going to be coated with antibodies. And whenever antigens in the blood are going to be attached to these antibodies on the cantilever, causes the micro cantilever to bend down like this. When there are no antigens to match the antibodies on the micro cantilever, it says it will be like a straight. There won't be any bend. So number of micro cantilevers with the different antibodies can be put side by side on a microchip so that you can diagnose the disease in the human body. Right? So this way, up to this point, you just see all these are generalized concepts which are just proposed. This is the, that means what are all the problems and is there any solution? But practically, few researchers implemented all these solutions, but still it needs to have the development, right? So in this way, that means all these, by seeing all these generalized concepts, so why should we take up this further? So, you know, after going through all these, if you're really impressed with these, you should provide some solution to the society where many people are suffering with many diseases. So here I'll explain the practical situation in the society, and then I'll explain where I'm motivated to take up some problems. So whatever the problems, real-time problems I have taken up, and I provided a small solution for that. So, you know, present scenario demands for highly sophisticated and consistent medical products, so that are going to be supported the timely needs of human beings, which are ever increasing, right? And today's technological breakthroughs, if you take in the fields of electronics, medical signal processing, instrumentation, and automation, which have led to design and develop a new devices that are considered as alternates and support to the doctors and physicians, right? So that again can assist and save human lives. So in this direction, miniaturization of the device has further lead to new generation treatments and medications which are fully automated and highly reliable. Right? And due to changes in human behavior and changes in the environment and changes in the inter-country relations, right? And human attitudes and non-availability of physicians, many scientists have come out with alternatives to meet these demands. So, you know, one of the major challenges you can taken up by many researchers is the design and development of biosensor for detecting the antigens responsible for the diseases. And you know, nowadays new viruses being detected in human body, which comes from the lifestyle of mankind, changes in the lifestyle of mankind. So for that, always required to take precaution and be prepared for any untowardness that can affect human body. So current day technology and the technologies to come up in future can be exploited to the benefit of human being. So in that direction, one of the areas in which the growth in technology can be fully utilized is the biosensor design and signal conditioning. Right? So till now, healthcare services from the government. Yes, ma'am.
Ma'am, you're not audible and your slides are also not moving.
Ma'am, slides are I'm changing whenever it is required. I'm changing. So these are all introduction I'm telling. I'm just discussing. So I'll come to the point. Okay, ma'am. So slides, don't worry. So now my voice is audible, ma'am.
Yeah, yes, ma'am. Yes, now it's audible.
Okay, fine, ma'am. So, till now, you just take the healthcare services from the government, so which were targeted at particularly rural areas, and particularly or more specifically at the poor people. So, in that direction, the national health policy shifts to universal health care, which means that everyone, irrespective of income, age, and employment, which will be covered by healthcare services. Even the Modi government wants to more than double the healthcare expenditure from 1.04% to 2.5% of the gross domestic products. You know? So there has been a steady increase in the usage of private healthcare facilities over the last 25 years for both outpatient and inpatient services, and both across rural and urban areas. And you know, nearly 44% of patients complained about the waiting period. And 52% said that there were no diagnostic facilities in government hospitals. So in that direction, many researchers came into the picture, and they have attempted in development of biosensors for these applications. So here we worked on various models of biosensors, which I'll show you in the coming slides. So here you're just looking at this diagram. This is the generalized diagram for biosensor. Right? So here a biosensor is a self-contained analytical device that combines a biological element, that is biosensing components. So with a physicochemical component, that is a biotransducer component. So to generate a measurable signal for detection of an analyte of a biological importance. So here this diagram is going to consist of three basic components, right? So you just see, one is a detector to detect the biomolecule and generate stimulus. And the second is the transducer, which is going to convert the stimulus to output signal. And the third is a signal processing system. So why signal processing system? To process the output and present it in an appropriate form. So basically, these biosensors here involve the quantitative analysis of various substances, by converting their biological actions into measurable signals. And a great majority of biosensors have immobilized enzymes. So the performance of the biosensors is mostly dependent on the specificity and sensitivity of the biological reaction. Right? And these biosensors are going to attach the significant interest in the last few years since the monitoring of a specific substance is essential in many applications. You can take from clinical analysis to environmental control. Right? So in this direction where I'm motivated and what is the need of these biosensors means the ability to detect pathogenic molecules, that means relevant molecules, which should have high sensitivity and specificity, which offers a powerful opportunity in early diagnosis and treatment of diseases. So due to the demand of doctors and assisting and supporting large human population, which is a challenging task. So therefore, here it is required that the human beings should be less dependent on physicians. So if we are going to have the less dependent on physicians, then who will detect the diseases? Right? So, and that too initial stages is the major dynamic factors of research. So a biosensor is a commonly defined analytical device that uses a biological recognition system to target molecules or macromolecules. So therefore, the need is to develop more efficient and reliable sensing and detection technologies. Therefore, the emergence of micro and nanoscale technologies for biology has a great potential to lead the development of next generation biosensors. So, and also with, you just remember, with improved sensitivity and automatically you should reduce the cost of the device. This is the ultimate goal. So, and at the same time, microscale biosensors may be more portable and scalable. For example, for point of care, sample analysis and real-time diagnosis, these micro-scale biosensors may be more portable. That is another advantage. Right? And at the same time, using this MEMS microcantilever technology and using finite element analysis tool, so biosensor model is designed and simulated becomes easy, right? So in that direction, you just see, for example, in India, human population is almost exceeding 1.4 billion in the year 2020. Right? So in Indian healthcare industry, which is growing at a rapid pace and is expected to become a 280 billion industries, $280 billion by 2020. Right? So this is the motivation. That means that these many huge in this huge population, how to the main problem is how to detect the diseases in the early stage. So for that, biosensors are one of the device which is going to play a vital role to detect the diseases in the early stage. Right? So you just take this graph. Right? So the point where I motivated towards this direction is the requirements of human needs with the advances in technology in detection of particularly cervical cancer. And for that cervical cancer, we have to give the solution with the biosensor based carbon nanotube field effect transistors. Right? And from this, you can see the time on one axis and number of cells, that is with the number of affected cells for cancer detection. Right? So at present, you just take the clinical detection threshold exists after reaching the patient in critical stage. This is current threshold for clinical detection. So almost the patients are reaching after this stage. So in order to detect the cervical cancer antigen with the non-availability of resources, practically I'm speaking, right? So through simulations and then fabrications, you can provide the solution, feasible platform for designing, modeling, and validation of the biosensors and signal conditioning circuits. Right? So why we are considering biosensors particularly? Right? So which is a cost effective and high sensitive biosensor is required for the detection of glucose levels, right? To satisfy the conditions, right? And even for cancer detection and any disease if you take. Okay, so this is what really the humans are facing a problem. So to overcome those problems, here the biosensors came into the picture. So what is the aim now, right? So here I'm entering into the actual concepts, actual work. So first thing is I would like to design the microcantilever biosensor for the detection of biomolecules. And I need to evaluate the performance of this biosensor, that is in terms of CNT FET array sensor with signal conditioning circuits. And the third is inkjet printer based biosensor for glucose detection. So 3 cases I have taken up. So one is microcantilever biosensor for the detection of biomolecules. Second is CNT FET array sensor with the signal conditioning circuit for cancer detection. And third is inkjet printer based biosensor for glucose detection. Right? So the main objective of this is you should review of different biosensors for biomolecule detection, and then different microcantilever modes and analysis of that means biosensors, and the analysis, design and analysis of this microcantilever based biosensors for the detection of biomolecules. So this is the first objective, right? So in that direction, this is microcantilever sensor for biomolecule detection. So here it also used to evaluate the performance of different types of nanobiosensors. Right? So, and here you will get the question that why microcantilever as a biosensor? That is microcantilever based biosensor. You know, cantilevers, if you take, you can design in any shape. There are plenty of shapes of these cantilevers. Right? So among all these, here the trapezoidal shaped cantilever structure is going to provide higher deflection than conventional rectangular microcantilever. So which is also proved. So that means the thickness, if you are going to consider the cantilever thickness, is the one of the geometrical parameter which decides the total deflection of the microcantilever. So here in my design, the thickness is chosen with the dimension of 50 micrometers in the existing design. That means that the cantilevers of smaller widths will have lower planar area, which has the edge effects. So because of that, the width of the microcantilever is increased gradually from the fixed end to the free end to form trapezoidal structure. Right? And at the same time, here I'm just optimizing the cantilever length and fixed in such a way that the total area of the proposed structure and existing structure should be equal. So we may ask the question, so if you are going to take the same, so what is the benefit? Definitely the proposed design is going to that means increases the linearity with the increment of beam length. So you know the beam width at fixed end is narrow as compared to width at the free end. So this is your fixed end and this is your free end. So in trapezoidal shape, the beam width at fixed end is narrow as compared to the width at the free end. So this width variation from fixed end to free end gives the trapezoidal shape of microcantilever beam. Right? So along with this rectangular shape paddle is introduced at the free end to improve the deflection. So I'll show the proposed designs also. So here the static mode of operation is performed in all proposed designs. Right? And in the second design, what I have done, the stepped square structure is introduced still to improve the output deflection. So all the proposed designs are having the same surface area, and the geometrical dimension in the proposed structure are optimally chosen to satisfy the total surface area also. Right? And also I have taken enough care that I maintain the same material for all the designs. Right? So in this direction, you just see the proposed structure. So there it has some tabular, that means values, micro cantilever design material with different values, right? So density of the material here, it is 2300 kg per centimeter cube, and Young's modulus 130 GPa, and the Poisson's ratio is 0.28. So by taking this into the consideration, this is the trapezoidal shape, that is a paddle trapezoidal type of micro cantilever beam design. This is design A. So you just see at a fixed end, you have the width is more when compared to the free end. Right? So, and here we represented with the different letters, and all these things are going to be, that means A, B, C, D, E values, how to calculate, and all these things we have to go with the micro cantilever design. So here the proposed design, the width of beam increases linearly with the increment of beam length, I already told you, and the rectangular paddle structure is introduced at the free end for better sensitivity and deflection. So the proposed structure is this. So here it is a trapezoidal micro cantilever structure which have the paddle area is present in the free end along with the trapezoidal structure to improve the total deflection. So antibody antigens interaction on this cantilever surface produces a surface stress. So with that stress, we can say that whether the diseased cells are present inside the body or not. So in order to determine the geometrical dimensions of this structure, the approximate magnitude and nature of this structure, that means stress, you should know initially. So if you know that stress, then the pressure produced by the injection of myoglobin protein, that means protein, which has 19.2 pascals, and the same surface area 50,000 micrometer square is considered for the design, and that means for the design. And this biomolecule equivalent 19.2 Pascal pressure is applied on the top surface of the proposed micro cantilever if you are going for simulation. Then only you will have the, that means this pad is going to have slight bend. Right? So how we determine the different parameters for this design, right? So initially the moment of inertia of a trapezoid, everyone knows. And if the total area is considered as rectangle by the length L and the width W, and the interior portion is divided into 5 smaller ones. That is, I already showed you A, B, C, D, E here. So the final moment of inertia of this design is going to be calculated by using this, and the radius of the curvature is this. So by using all this, you can design the paddle trapezoidal type micro cantilever beam, right? And the simulations, after simulation of this design, the total displacement of the proposed paddle trapezoidal micro cantilever beam is with the surface, that means surface area, by taking the surface area as 50,000 micrometer square with the pressure 19.2 pascals. And the output total displacement of the proposed paddle is 0.3741 nanometers. So that means that the output deflection is improved because of the paddle structure we introduced at the free end. So I'll compare this with the existing systems also. Right? So now come to the design B. So here, that means a square step paddle trapezoidal type. So you just observe at the free end, not at the fixed end. Fixed end is same as the previous one. Free end, if you look at that, so you can see that there is a square. So, and the size of the square is 50 micrometers by 50 micrometers by 50 micrometers. So why we introduced like this? Means the surface area, to make the surface area as constant. So the proposed cantilever design and structure, we are considering the thickness of this paddle is 50 micrometers, which is same as the previously discussed thing. Only the difference is this at the free end. Okay, so this is the proposed actual design. Okay, so here the square I already told you. So width, length and thickness, we have taken 50 micrometers, right? So, and we introduced this at the free end, right? And such that the surface area is going to be constant. And here you can also observe that the square step paddle trapezoidal micro cantilever structure, the paddle area is at the free end, and the moments of inertia of a trapezoid you can find out if the total area is considered from this as rectangle by the length of L and the width W, and the interior portion is divided into same as previous one, like A, B, C, D and E, right? So here also the same design formulas we used, and we designed this structure. And when we come to the simulation, here also the surface area is going to be 50,000 micrometer square with the pressure, same pressure we applied. And the output, if you observe, which is going to be 0.43837 nanometers. That means the output deflection is improved because of the stepped structure in the fixed free end, and paddle structure is introduced at the other end. So if you compare all these, so paddle trapezoidal microcantilever structure, right, and with the stepped paddle trapezoidal microcantilever structure, you know, the rectangular structure is going to provide the deflection, free end deflection as 0.110 nanometers, right? But by applying the same pressure, that is most important one, that is 19.2 pascals. So here that is conventional rectangular microcantilever is giving the deflection of 0.110, right? So whereas a paddle trapezoidal theoretical value is 0.3614, but after simulation we have 0.3741. Whereas stepped paddle 0.478 and it is 0.4387. So from this, you can conclude that the deflections for the proposed micro cantilever designs have better sensitivity and deflection, right? And even you can compare with the theoretical values. Okay. So this is the comparison with the existing rectangular microcantilever, and this is existing trapezoidal microcantilever, and the green represents the proposed design, and the purple is proposed design B. Right? So in all the designs, a deflection, if you observe at the micro cantilever, so here the surface area, right? So the that means it has a large surface area at the free end of beam as compared to fixed end of beam, right? So the biochemical reaction in this biosensor is relatively large due to more number of bindings at the micro cantilever at the free end. Right? So, and also this is having nearly twice than conventional designs. That means a deflection. I'm in terms of what I mean, and detects the analyte with high sensitivity. Okay. So the stress analysis of different molecules I have taken up. So viruses for HIV-1, human adenovirus, and tobacco mosaic virus. For these three viruses, the mass is like this in kg, and force in Newton is this, and the stress in that means the newtons per meter square for rectangular design is going to be this. That means 5.6393 into 10 power minus 8. And whereas for design A, proposed design, 1.505 into 10 power minus 7. And design B is 1.673 into 10 power minus 7. And similarly for human adenovirus, you just observe here. So the stress is 1.4098, right? And it is having 3.762 into 10 power minus 8, and here it is 4.184 into 10 power minus 8. So similarly for tobacco mosaic virus. So by considering all this, we can say that the proposed design B is having higher sensitivity when compared to the existing or even proposed design A. Right? So in this problem, you can conclude that in order to design high performance micro cantilever based biosensor for biomolecule detection, so the existing rectangular micro cantilever property and deflection is reviewed and derived the equations from the Stoney's equation to find the total deflection at the free end of the micro cantilever. So all these we have done through the COMSOL multiphysics software. And here after the investigations, the role of virus shapes in microcantilever sensitivity, and identified that by introducing paddle at the free end of the microcantilever, the sensitivity and output deflection could be increased. Right? And also we just derived moment of inertia and free end deflection for proposed paddle trapezoidal microcantilever for both design A and design B. So if you take the relationship between the pressure due to biomolecules and total displacement, which is represented for existing and proposed designs. So finally, you can see that through these simulation results, the proposed stepped paddle trapezoidal microcantilever produces the total displacement at the free end increases nearly twice than the existing designs because of increased surface area at the free end. So therefore, finally, I can say that the proposed structure gives the better deflection and it detects the analyte with high sensitivity. Okay. So coming to the next problem, that is CNT FET biosensor for signal conditioning circuits, particularly for cervical cancer detection. You know, before going to enlighten the CNT FET array, how it is going to detect the cervical cancer and how it is going to perform the signal conditioning circuit, you should know about the cervical cancer, right? So you just take the WHO report, that is World Health Organization. So in that, always the top diseases for particularly for women, if you take, so first and second, almost it is going to be like 6 months, like cervical cancer will stand at first position and breast cancer will be the second, or else breast cancer will be the first and cervical cancer will be the second. So because of this cervical cancer, most of the women are affecting and which is growing at a very significant rate. So in that direction, one of the major challenges in treatment of cervical cancer is cervical cancer detection in their early stages. So that means that the use of cervical specific antigen, that we simply call it as CSA, you have to go with the test. So which is, if you go under test, which has aided the prediction of cervical cancer risk and treatment outcome. So which is important to develop an ultra sensitive and selective biological sensor for cervical specific antigen detection. Right? So which, if you are going to propose some biological sensor, so that is going to allow the early detection of cervical cancer, which is going to be expected to improve preventative health cares. Right? So, and you know where these cells are going to be accommodated in a human body, right? So the cells which are lining the cervical part, that is in the lower side of the womb. You can also called as the transformation zone, and that is going to be affected and causes the cervical cancer. You know, first these cells in the transformation zone, first it is going to change into precancerous cells and then to full grown cancer cells, right? And these precancerous changes are termed as a cervical interpithelial neoplasia, that is a CIN. And squamous lesion, and you can also call it as dysplasia. and which can be detected present by using papilloma virus, pap smear test. So, there are two types of cervical cancer, right? So one is a squamous cell carcinoma, and the other one is adenocarcinoma. So first one is going to form from the cells in the exocervix, and the cancer cells have features of squamous cells. The second type of cells, that is adenocarcinomas, which develops from gland cells that are in the exocervix. That means that the precancerous cells are going to change to full grown cervical cancer cells over time period. And if you have smoking and human papilloma virus infections, or the major causes of cervical cancer that risks precancerous cell to cervical cancer cells. And here the HPV is a kind of virus that infects the skin lining of genitals, anus, and mouth and throat. Right? And you know, HPV can also spread from one person to another person with the contact. So the high risk type of HPV, such as for cervical cancers, that means particularly I'm talking about. So 16 and HPV 18 are very well known for cervical cancers, and most prominent virus is HPV 16 and HPV 18, which causes cervical cancer. So see, nowadays, if you go for the master health checkup, it is this pap smear test is included in the list of tests in the master health checkup. So why this pap test particularly? So which is used to check for HPV virus. Even DNA is checked from HPV cells for cancer detection. Right? And the pap test and HPV test are the most famous tests for cervical cancer and is recommended to be carried out frequently. But if you take the, that means, efficiency or performance or sensitivity is very, very less with this test. Right? So from that, the most widespread techniques for detecting cervical cancer are based on the enzyme-linked immunosorbent assay, that is nothing but ELISA test. Right? So here, even if you want to go with ELISA test, so those techniques, you need expertise on those techniques in molecular biology and which are going to be performed by first immobilizing an unknown amount of antigen on the substrate. Right? So here, to detect the antibodies with an affinity for the unknown antigen are going to be added, and these antibodies are pre-labeled with an enzyme. Right? So how we are going to add this means by bioconjugation process. Right? So like this, the CNT FET-based detection offers significantly lower quantifiable detection as well as fast and all electronic readouts that can be performed by any technician in a point of care diagnostic settings. Right? And this cancer detection is one application of sensors. right? And this is that means particularly cervical cancer is a major public health issue, and detection of early stage cancer often results in successful treatment with long term disease free. Almost it is present in the 60 to 90% of patients are there, right? So here, because of that, that means the carbon nanotube field effect transistors provide a unique platform for biosensing applications. So you may ask the question, why is only CNT-FET? See, in this CNT-FET, every atom is on the surface, and carbon nanotubes are sensitive to small changes in their immediate surroundings. That is the beauty behind this CNT-FET. Right? So in that direction, we are taking CNT-FET as the biosensor model for this cancer detection. Right? So these are the different characteristics with the different electrical parameters. That is generalized one. And here there is a comparison of silicon nanowire MOSFET, then CNT-FET MOSFET, and what is the improvement between these two. So if you take the transconductance, you see 27% of the improvement is there between these two. And output conductance, if you take, it is 23%. Voltage gain also, 6% of voltage gain improvement is there. And 32% on current. So CNT-FETs are promising devices with superior characteristics as compared to silicon nanowire MOSFETs. Right? And also it has a better improvement when compared to the silicon nanowire MOSFETs. Right? So here it is the modeling of CNT-FET. As you know, the CNT-FET, which consists of source, gate, drain, right? And the performance functioning of this CNT-FET, I'm not going to stress on this. So particularly the CNT-FET is going to be used for major cancer affecting women. That means to detect at early stages. So this is the model which we proposed. It is not there in anywhere, right? So CNT-FET array sensor and signal conditioning. This is very important. Without signal conditioning, you cannot obtain the output. So here, the proposed sensor is designed with 3 groups of sensors, and we have signal conditioning circuits, which all these are responsible to provide maximum performance in detecting the CSA. Right? So, and here we used back gate and top gate biases. We set to achieve maximum current flow in CNT-FET. And here we proposed 8x8 CNT-FET array with double gate. And with that double gate, along with the double gate, we proposed current mirror and differential amplifier for signal conditioning for the detection of cervical specific antigen. Right? So these are the 3 groups of sensors I told here. So the same thing, periphery sensor connection and core sensor connection and middle sensor connection. So by using these 3 sensor connections, we are going to have the 8x8 CNT-FET array. So these are the device properties of CNT-FET. And 8x8 CNT-FET array, so based biosensor here we proposed, and here these biosensors having 8x8 means our total 64 sensors are going to be grouped into 3 modes, such as core sensor, middle sensor, and periphery sensor. So under backgate bias voltage, we consider it as 0.4 volts, 0.2 volts, and 0 volts, which are set to 3 groups of sensors that provide maximum current flow with improved sensitivity. right? And these connection of these three groups of sensors provides maximum current flow with any changes in top gate voltages, any changes in these voltages, right? And for signal processing, so we have given the signal processing circuitry. Through that circuitry, we are going to obtain the output. So this is 8 by 8 sensor array here we proposed, and here you just see the green represents 1 to 9, that is S1, sensor 1, sensor 2, sensor 9, then 7, 8, 16, and then 49, 57, 58, then 56, 63, 64, which are periphery sensors, right? And all these sensors are connected internally, right? So which is nothing but 12 CNT FETs. And then you come to the yellow shade. So yellow shades are nothing but we are termed it as middle sensors, and almost these are like 20 CNT FETs, right? And all other remaining sensors, that is middle, right? So which are 32 of them are termed as a core sensor, which are connected, right? So these sensors that are in periphery are connected with the backgate voltages of 0 volts. Sensors that are in middle are biased with the backgate voltage of 0.2, and the core sensors are connected with backgate voltage of 0.4 volts, right? So these are the results obtained from the CNT FET based biosensor, right? Quickly, I'll go through it. So this is the model what we designed. From this the results are obtained like this. So the output signal is inverted to the input and amplified from 0.69 volts and 0.88 volts due to perfect input biasing, right? So here the traditional method causes embarrassment to the woman, right? So whereas proposed method is by using urine or blood sample, you can do the test. And sensitivity, if you consider here, improper handling of samples and devices, whereas here this happens due to charge transfer process, right? So in this that means what I conclude before going to this is the properties of carbon nanotube, right? So which is that means designed CNT FET, designed CNT FET sensor array and signal conditioning circuits for cervical cancer detection, and proposed array sensor network is demonstrated with a different group of sensor networks like core, middle, and periphery, and enhanced output, right? So then come to the third part, which is inkjet printer based sensor and signal conditioning circuit. Quickly, I'll go through this because time is already 3:35. So I think Vimla ma'am.
Yes, ma'am.
Shall I continue?
Yes, ma'am. Participants, you have to give some time for the participants to ask questions, ma'am.
Okay, ma'am. Within 10 minutes, I'll close and I'll give the time.
Yes, thank you, ma'am.
Yeah, thanks. Right. So here, the inkjet printer based biosensor for glucose detection. Okay. So we can say that here the inkjet printing is the versatile method which allows the deposition of ink in very small volumes. That means you can also say that in terms of picoliters in a rapid manner, with high pattern precision and resolution. Right? So glucose oxidase, which are going to be considered as electron donors, and a conductive silver preparation numbers like I'll show you 0.50 is specifically designed for screen printing application on flexible substrate like polyester, polycarbonate. You can also take a polyamide and even ceramics. So what are the applications of this? Means where silver nitrate is used or in membrane touch, keyboards and switches, PCB track jointed, low flexible voltage circuitry substrates, flexible PTF resistor inks and brushing ceramics, brushing ceramic substrate for electroding. Right? So these already we fabricated this inkjet cartridge, right? So for glucose detection. So these are the parameters we considered, that is print output speed and resolution, and each dot, I mean drop volume of each dot, and printing dot size, and method, what method used for printing means a drop on demand thermal inkjet printer we considered. Right? So this is the block diagram of experimental setup. Right? So printed pattern sensor, which is going to be Wheatstone bridge, and if bridge is balanced, then we are giving it to the signal conditioning circuit, and finally it is going to display. So this is the inkjet printer, what we considered, and this is the design of serpentine structure, right? So and which is also in circular shape, and this is the experimental setup. So I mean by using this the circular pattern, why we have chosen circular pattern of biosensor, that is fabricated using inkjet printer, which has better output current, which shows the better sensitivity, and is tested have highest sensitivity compared to the existing method. So with this circular structure, which is reliable than the serpentine structure, as it has improved sensitivity in glucose detection. Right? And the results here we compared with the existing system, and the current change of current is better in the proposed system. So you can also see this diagram. The blue is existing for glucose concentration, and this is serpentine structure, and this is circular structure what we proposed. So from this, all the three kinds of biosensors we designed and we proposed for three different biomedical applications. And finally, what I should conclude from this is every day you just see technology is changing, or we can say that technology will change our lives and the way we conduct our day-to-day activities. And you know, the major technological breakthroughs always will be interdisciplinary, and it occurs at the fringes of classical disciplines, that is bio, info, nanotechnology. So all the engineers, scientists and technologists will need to be trained with depth as well as breadth. Right? And after seeing all these things, you can conclude that it is a cost-effective and efficient manufacturing techniques we have, and processes will play a pivotal role in determining whether a technology is merely a laboratory curiosity or whether it can be commercialized. That means the technology will affect our future as yet unimagined ways. So finally, I can say that the best way to predict the future is to invent it. So thank you. If you have any questions, you please.
Any questions from the participants?
Yeah, ma'am, this is Srini here, and you mentioned that inkjet printer was used. Where did you do that fabrication method, man? And
In
what
my
is the machine?
laboratory.
So
In
do
my
you have
laboratory, only with the inkjet printer. So that means the carbon we have taken, and with that carbon we designed on a paper, on a white paper we designed that structure with the carbons, and we connected with the input and output, and we taken printout from the inkjet printer with the material I said, no. So this is a very simple experiment you can do in your laboratories.
with the normal paper printing you are talking about?
Normal paper printing.
Oh, okay.
Yeah.
So only the cartridge you have used different ink from
Yes.
what we have mentioned there, silver and
Yes.
nitrile
Yes.
ink.
Exactly.
Okay, thank you. Thanks.
Yeah.
Akshay, conclude.
Yes, ma'am. Good evening, all. I, on behalf of Head of Department of thanks the speaker, Dr. AICTE ma'am, for today's talk. I would like to thank you, ma'am, for virtual visiting and enlightening us with your research in sensor models for biomedical applications. It really gave us a deep insight into the topic and also revealed some interesting facts. To express our sincere thanks for giving an excellent coverage to NEMS and its application, motivations and needs, designs, simulation, modeling of CNT, FET array sensor for cervical cancer detection, design inject detect glucose concentration. I'm sure the knowledge that you gave us will definitely help us in studies in biomedical sensor, ma'am. Thank you once again. Also, thanks to all the faculties and research scholars present here for paying attention and learning. Thank you. Thank you all. Thank you, ma'am.
Thank you.
One participant has posted some doubts in the chat box, ma'am.
Yeah, please, ma'am.
No, I think it is in the chat box.
How do you compare these sensors repeatability? The question is in confusion state.
Yeah, it's not very clear actually.
It is not clear actually. Sensors comparison we can do with existing devices theoretically first thing, and then you can compare with simulations and fabrications, and then I mean practical sensors you can take and you can compare repeatedly. So
thank you for your
I
time.
think thank you, ma'am. Thank you, Vimla, ma'am, for giving me the opportunity.
Can we visit your lab, ma'am? Is that
Yeah,
possible?
ma'am. Always.
Not during this time, but little later.
Yeah, no, ma'am. Next month, February and March first week, till March first week. So
Okay.
you can visit the lab, ma'am. But a prior intimation is needed, ma'am. At least 1 week.
Oh, sure, ma'am.
Yeah.
Thank you, ma'am. Thank you so much,
Yeah.
ma'am.
Thank you, all the participants, for patiently listening my talk. Thank you so much.
You can sign out, ma'am.
Yeah, thank you, ma'am. Yeah.